All right, get ready, everyone, because today we are diving deep, deep into the world of receptor pharmacology. We're going to be kind of exploring the language of it all, the very terms that scientists and researchers use to really get a handle on how drugs do their thing in the body.
Yeah, exactly. And, these terms, they can be a little intimidating at first, kind of a mouthful, but they are absolutely crucial if you want to really understand how drugs work, their actions, the side effects, and even, how our own bodies function
Hmm.
at the molecular level.
Exactly, and we've got some really cool research articles that we're going to be using to guide our exploration. So are you ready to uh, decode all this jargon and uncover some really interesting insights?
Oh, absolutely. Let's jump right in.
Okay, let's start with maybe the most basic term, the receptor. I mean, we hear this word all the time, but what does it really mean in like the world of pharmacology?
All right, so you can think of a receptor as this tiny little protein. It's super specialized, it sits on the surface of a cell, and it acts like a lock, waiting for the right key. And that key is a specific molecule, which could be a drug, could be a naturally occurring substance in the body. And we call that the ligand.
So it's like a molecular matchmaking service. The
Right.
receptor is picky, only interacts with certain ligands that fit its unique shape.
Exactly. And when that perfect match happens, when the ligand binds to the receptor, it sets off this whole cascade of events inside the cell. It's like signal transduction. It sets off this chain reaction that leads to a specific biological response.
That's pretty wild, and I'm guessing this is how our bodies, how they regulate so many different functions,
Right.
from breathing to emotions to even falling asleep.
You got it. It's all about those receptors getting the right signals from those ligands, and then
Yeah.
they kick off the right actions inside our cells.
Okay, so let's talk about the keys then. The ligands that activate these receptors. Now, in the research on adenosine receptors, I came across this term agonist. Could you break that down for us a little bit?
Sure. So an agonist is a type of ligand. It binds to a receptor and activates it, which then, triggers that response. So it's like that key that fits perfectly into the lock and it opens the door to all this cellular activity.
Okay, so the agonist is the one that gets things moving. Now, I remember reading about a specific agonist called SDF1A, and it activates the CXCR4 receptor. And then there were also all those adenosine analogs like NECA, GHA, 2-keto, and RPIA, and they're all agonists, but they seem to have different effects on breathing.
Yeah, that's a great observation, and it really highlights something important. See, different agonists, even if they bind to the same receptor, they can have different levels of effectiveness, right? And we call that efficacy. It's a measure of, how well an agonist can actually activate that receptor and trigger a response once it's bound.
So one agonist might be like a gentle nudge to the receptor, while another one is like a full-on shove, leading to a much stronger response.
Yeah, that's a great way to put it. And understanding that efficacy of different agonists is really important when we're developing drugs. We want to produce the right level of response without causing, a bunch of unwanted side effects. It's all about finding that sweet spot where the drug is effective but also safe.
Okay, that makes sense. But what about the molecules that don't want the receptor to be activated? What do we call those?
Those are our antagonists. You can think of them as like blockers or even decoys. They bind to the receptor, but they don't activate it. So they actually prevent the agonist from binding and triggering a response.
So they're like putting gum in the lock to prevent the actual key from turning.
Haha, exactly. And antagonists are just as important as agonists, when we're developing drugs, because they allow us to block, specific cellular processes that might be causing a disease or a condition.
I remember reading about this drug called theophylline. It's used to counteract the respiratory effects of some of those adenosine analogs. So it sounds like it's working as an antagonist in that case.
That's right. Theophylline is an antagonist. It competes with those adenosine analogs for, binding to those adenosine receptors, and this competition helps to reduce those respiratory effects.
Okay, so we've got agonists, the activators, and antagonists, the blockers. Now, when I was going through this research, I also saw terms like affinity and selectivity,
Mm.
and they seem to describe, how a molecule interacts with a receptor. Could you explain those a little bit further?
Absolutely. So affinity refers to how strongly a molecule actually binds to its receptor. It's like how snugly that key fits into the lock, right? So a molecule with high affinity, it binds tightly to its receptor, like a perfect match, while a molecule with low affinity, it binds weakly, like a loose fit.
So I'm guessing higher affinity is usually a good thing when it comes to, to drugs. It means you need a lower dose to get the effect that you want.
That's often the case, yeah. And it's why researchers are always trying to develop drugs that have a higher affinity for their, target receptors. They want to maximize the drug's effectiveness while also minimizing the amount that's needed, which can help reduce those side effects.
That makes sense.
Yeah.
Now, what about selectivity? How does that relate to affinity?
Okay, selectivity is all about how specifically a molecule binds to one type of receptor over others. So it's like having a key that only works on one specific lock. It won't fit in any others.
So a highly selective drug is like a precision tool, right? It targets only the receptor that it's meant to, and that minimizes the chances of hitting, unintended targets, which could lead to those side effects.
Exactly. And in the research on adenosine receptors, you'll see a lot of discussion about the selectivity of different drugs, for the A1 versus the A2 subtypes of adenosine receptor.
Right. I noticed that, for instance, there was a lot of focus on modifications to the structure of xanthine antagonists, right?
Yeah.
To make them more selective for A1 receptors.
Exactly. Scientists are, constantly working to tweak that chemical structure of drugs to improve their selectivity. And it's a crucial part of drug development because it allows us to create therapies that are more targeted and therefore potentially safer and more effective.
This is all so fascinating. I'm starting to realize just how much detail goes into understanding how drugs work in the body.
Oh, it's a complex field, definitely, but it's also incredibly rewarding. The more we understand about these molecular interactions, the better we are at developing treatments for a wide range of health challenges.
Okay, so we've got receptors, agonist, antagonist, affinity, selectivity. These terms are already giving me a much clearer picture of how these drugs are interacting with the body. But I'm sure there's a lot more to uncover. What other key terms should we add to our pharmacology decoder ring here?
Well, we've only just scratched the surface. There are a few more fundamental terms we need to cover before we can really, dive deeper into the more complex aspects of receptor pharmacology.
All right, great. Let's keep going. What's next?
Let's talk about efficacy in a little more detail. We touched upon it briefly when we were talking about agonists, but it's such an important concept, it really deserves its own spotlight.
All right, remind me, what was efficacy again? I remember it had something to do with how effective an agonist is.
Right, so efficacy is the maximum effect a molecule can produce when it binds to and activates a receptor. It's a measure of, how well an agonist can turn on the receptor and trigger that downstream signaling cascade.
So two agonists might bind to the same receptor, but one might be better at triggering a response than the other.
Exactly, yeah. It's like having two keys that both fit into the same lock, but one might only open the door a crack while the other one swings it wide open.
Uh-huh. That's a great analogy. Now, I remember reading about morphine and how it acts as a lower efficacy agonist at the mu opioid receptor.
Oh, perfect example. And sometimes a lower efficacy agonist like morphine can actually be beneficial.
Oh, really? Why is that?
Well, research suggests that that lower efficacy agonists might cause less receptor desensitization, which means that the receptor, stays responsive to the drug over time, and that reduces the risk of tolerance and dependence.
So in the case of pain management, using a lower efficacy opioid like morphine could help control pain effectively while, minimizing that potential for addiction.
Exactly, yeah. And it highlights why understanding this whole concept of efficacy is so crucial, for tailoring those drug treatments and making informed decisions about, which medications are best for different patients and different conditions.
Okay, efficacy is definitely making more sense now. So we've got efficacy, which is about the maximum effect. What about potency? Is that how strong a drug is?
Potency and efficacy are often confused. but they are distinct concepts. Potency refers to the amount of drug that's needed to produce a specific effect. It's a measure of, how much drug is required to achieve a certain level of receptor activation.
So a highly potent drug might only need a tiny dose to,
Hmm.
to achieve the effect that you want, while a less potent drug might need a much larger dose.
Exactly. And potency is influenced by both affinity and efficacy. So a drug that has high affinity and high efficacy is going to be more potent than a drug with low affinity or low efficacy.
So it's like some keys might be really good at turning a lock, right? High efficacy. But you might need to use a lot of force to turn them. That's low potency. While other keys might turn that lock really easily with just a gentle twist. High potency.
Right.
Because they fit perfectly and are designed to to maximize that leverage.
Haha. That's a great way to visualize it. And
Right.
in the research on adenosine analogs, there are some great examples of potency comparisons. For instance, the study on respiratory depression in rabbits showed that the potency of those analogs follows a clear ranking. NECA is the most potent, followed by CHA, and then 2-keto and RPIA, which have similar potencies.
Interesting. So even though those analogs all target the same receptor, their potencies can be pretty different.
Absolutely. And those differences in potency are important considerations when we're, developing those drugs. We need to understand how much of a drug is needed to get that desired effect. And we also need to think about the potential for side effects at different doses.
Okay, potency is starting to click for me now. So we've got efficacy, which is about the maximum effect, and potency, which is about the dose needed to achieve that effect. What other key terms should we explore?
Okay, there are two more terms that come up a lot when we're talking about receptor pharmacology: desensitization and internalization. And these are really crucial for understanding how those receptors respond to, prolonged or repeated exposure to drugs or ligands.
Ooh, those sound intriguing. What exactly do they mean?
Okay, think about, what happens when you use the same key on a lock over and over again. Eventually that lock is going to get rusty and the key might not turn as easily. And that's kind of what happens with receptor desensitization.
So the receptor becomes less responsive to the drug, even if the drug is still binding.
Exactly. And it's a natural process. It helps protect cells from being overstimulated.
Ah, so it's like a safety mechanism
To
to prevent the cell from being bombarded with signals.
Exactly. But desensitization can also lead to, that phenomenon we call drug tolerance, which means that you need, higher and higher doses of a drug to achieve the same effect.
Okay, that makes a lot of sense. I'm starting to see how all these terms are interconnected.
They are. And that interconnectedness is what makes, receptor pharmacology so fascinating and complex.
Okay, so desensitization is like a rusty lock that's gotten less responsive.
Yeah.
What about internalization?
Okay, internalization is like taking that rusty lock and hiding it away in a drawer for a while. It's a process where the cell physically removes the receptor from its surface and basically takes it out of commission for a bit.
Wow, so it's like the cell is saying, okay, this receptor needs a break. Time for a timeout.
Exactly. And internalization is often a step that follows desensitization. It's a way for the cell to further regulate that receptor activity and prevent too much signaling.
And I'm guessing there are specific examples of this in the research.
Absolutely, yeah. The research on CXCR2 receptors is a great example. Studies have shown that when this receptor is stimulated with a ligand called CXCL8, it undergoes phosphorylation, and then that triggers internalization and desensitization.
This is also fascinating. It's amazing to think about all this, intricate action happening at the molecular level,
Yeah.
all orchestrated by these tiny receptors.
It truly is remarkable, and we've only just begun to explore all the complexities of receptor pharmacology. There's a whole world of fascinating mechanisms and interactions that we haven't even touched on yet.
Well, I'm definitely eager to dive deeper. But before we move on,
Right.
maybe we should do a quick recap of all the key terms we've covered so far.
That's a great idea. Let's make sure we're all on the same page before we venture, further into this world of receptor pharmacology.
Okay, so we started with the receptor, the lock on the cell surface that interacts with specific molecules called ligands. Then we learned about agonists, which are the keys that activate those locks, and antagonists, the decoys that block them.
Right. We also talked about affinity, how strongly a molecule binds to its receptor, and selectivity, how specifically it binds to one type of receptor over others.
And we got into the details of efficacy, which is the maximum effect an agonist can produce, and potency, the amount of a molecule that's needed to achieve a specific effect.
And finally, we explored desensitization when the receptor becomes, less responsive over time, and internalization when the receptor is pulled into the cell, taking a temporary break.
Wow, that's quite a list. But thanks to your expert explanations and those vivid analogies, I feel like I've got a pretty solid grasp on these concepts now.
I'm glad to hear that. These
Yeah.
terms are truly the foundation for understanding how drugs interact with the body, and there's still so much more to explore.
I know. It's like we've just opened the first page of a really fascinating book.
Exactly. And as we turn the pages, we're going to uncover even more intricacies and complexities in this world of receptor pharmacology.
I can't wait. But for now, I think it's time to take a little break and let our listeners digest all this incredible information. We'll be back soon to continue our deep dive into this remarkable field.
Welcome back, everyone. Now that we've got those core terms down, we can really start digging deeper into this fascinating world of receptor regulation.
Okay, I'm ready for more. Before the break, we were talking about desensitization and internalization, the ways that cells kind of modulate that receptor activity
Right.
to prevent overstimulation.
Right, and those processes really highlight a critical point. These receptors, they're not just static things. They're not just stuck on the cell surface. They're dynamic, constantly being adjusted and fine-tuned by the cell.
So it's not just a like an on or off switch. It's more like a complex dance, right, between the receptors and the cellular environment.
Exactly, yeah. And one of the key regulators of this dance is what we call receptor trafficking. It's the movement of those receptors within the cell.
Wait, so the receptors aren't just fixed in one place on the cell membrane. They can actually travel around.
Oh, absolutely. Think of it like a bustling city, right? With receptors constantly being shuttled to different locations, the cell surface, internal compartments, all depending on what the cell needs at that moment.
Okay, I'm picturing tiny little molecular taxis,
Yeah.
right, zipping those receptors around the cell. So what decides where these receptors need to go?
A lot of different signals. It could be the binding of a ligand, changes in the environment of the cell, even signals from other receptors.
So the cell is constantly monitoring its receptors, like an air traffic controller, right? Making sure they get to where they're needed most.
That's a great analogy. It's really a remarkable feat of cellular orchestration, and it plays this crucial role in regulating how sensitive a cell is to a particular drug or molecule.
This makes me think about how some medications they seem to become less effective over time. Could that be because of this receptor trafficking?
It's definitely possible. You see, if a receptor gets internalized, it's basically hidden from the drug, right? So that reduces the cell's sensitivity, and that's one of the mechanisms that can contribute to drug tolerance.
Okay, that makes sense. But what about the opposite? Can a drug actually increase the number of receptors on the cell surface?
Yes, that's possible too, through a process called receptor upregulation. So certain drugs or even certain conditions, they can cause the cell to produce more of a particular receptor, and that increases its sensitivity to that molecule.
So it's like the cell is saying, hey, I need more of these receptors to deal with this.
Exactly. Upregulation is often, like a compensatory mechanism. So, for example, if a receptor is being blocked chronically by an antagonist, the cell might try to counteract that blockade by making more of that receptor.
Wow, our cells are pretty clever. It's like this constant tug of war between the drugs we take and our body's own regulatory mechanisms.
Indeed, and this really highlights, why it's so important to understand that the dynamic nature of receptors.
So we've talked about receptor trafficking and upregulation. Are there any other ways that that receptor activity can be, kind of modulated?
There are. Another really fascinating one is what we call receptor dimerization.
Dimerization. What does that mean?
It means that, two receptors, they can actually pair up. They form what we call a dimer. And this pairing can really significantly alter, how they function.
So it's like two receptors, joining forces. They become like greater than the sum of their parts.
Exactly. Dimerization can, it can change how those receptors bind to ligands, how they signal, even how they're trafficked.
Wow. So that's adding like a whole other layer of complexity to this intricate receptor dance.
Yeah, absolutely. Yeah. And research on dimerization is really opening up some exciting new avenues for drug development. Imagine you're designing drugs that specifically target these dimers, right? Rather than individual receptors.
That's incredible. It could, it could lead to therapies that are even more precise and targeted.
Exactly. It's all about, understanding that intricate language of receptors and then using that knowledge to develop smarter, more effective medications.
Okay, I'm ready for another key term. What's next on our pharmacology glossary here?
Let's talk about allosteric modulation. This refers to a molecule binding to a site on the receptor that's different from the main binding site. The one for the agonist or antagonist.
So it's like there's a secret back entrance to the receptor.
Exactly. And this allosteric binding, it can really subtly influence the receptor's activity in a variety of ways.
So instead of directly activating or blocking the receptor, an allosteric modulator is more like tweaking the receptor settings.
Yeah, that's a great way to put it. They can enhance or reduce the effects of those agonists or antagonists. They can even change the receptor's affinity or efficacy.
Wow, that's pretty powerful. It's like having a fine-tuning knob, right, for receptor activity.
Precisely. And this opens up so many possibilities for drug development. Imagine designing drugs that act as allosteric modulators.
Yeah.
Fine-tuning that receptor activity in a much more subtle and precise way than those traditional agonists or antagonists.
That sounds like a really promising approach for developing therapies with fewer side effects.
It certainly has the potential. Yeah, allosteric modulation, it lets us target those receptors with much greater precision and control, which could lead to more effective treatments with a much better safety profile.
This is all so fascinating. It feels like we're peeling back the layers of an onion here, uncovering more and more complexity with every new term.
I agree. And this complexity, it's what makes receptor pharmacology so challenging, but also incredibly rewarding. The more we understand about these intricate interactions, the closer we get to really unlocking the full potential of this whole field for developing new and innovative therapies.
Okay, I'm ready for another challenge. What's next on our list of key terms here?
Okay, let's delve into this concept of biased agonism. This is a relatively new concept, but it's generating a lot of excitement in the field.
Biased agonism. That sounds intriguing. What does it mean?
Well, traditionally we thought that an agonist it would activate all those signaling pathways downstream of a receptor, equally.
So it's like flipping a switch that turns on all the lights in a room at the same time.
Exactly. But now we're starting to realize that some agonists are actually biased. They preferentially activate certain signaling pathways over others.
So it's more like having a control panel where you can pick and choose, right? Turn on certain lights while leaving others off.
You got it. Bias agonism. It's a remarkable discovery, and it's really changing how we think about drug development.
Okay, I'm trying to wrap my head around this. So two different agonists, they could bind to the same receptor, but one might trigger pathway A and the other one triggers pathway B.
Exactly, yeah. And that has huge implications for how we design drugs.
Because you could design a biased agonist that only targets the pathway that you want to activate, right?
Uh-huh.
And that would minimize those unwanted side effects.
That's the idea. Biased agonism is a real, game changer for developing those more targeted and effective therapies.
This is incredible. It's like opening a door to a whole new world of possibilities.
I agree. Biased agonism is really, revolutionizing how we think about receptor pharmacology.
Okay, I'm feeling like a real deep diver now.
Yeah.
We've covered so much ground, and I'm starting to see that bigger picture of how these receptors work.
You're doing great. We've gone through a lot of key terms, but there's still a few more that are really essential if you want to understand receptor pharmacology.
Okay, bring it on. I'm ready for the next challenge.
All right, let's talk about constitutive activity. Now, this refers to the fact that some receptors they can actually be active even without a ligand.
Wait, what? So a receptor can be signaling even if there's nothing bound to it?
Yeah, exactly. Yeah, it's like a light switch. It's always partially on, even when it's flipped off.
That's wild. I thought receptors they needed a ligand to be activated.
That's the traditional way of thinking about it. But we now know that some receptors they just have this inherent ability to be active on their own.
Okay, so constitutive activity is like a baseline level of receptor activity.
Precisely, and it can vary between different receptors. Some some have very low constitutive activity, while others have high constitutive activity.
So if a receptor has high constitutive activity, it's like that light switch is always halfway on, even without a ligand.
Exactly, and this can have some important implications for drug development. Imagine designing drugs that specifically target these constitutively active receptors.
That's fascinating. So you could potentially develop drugs that either enhance or reduce that constitutive activity, right?
Right.
And that would fine tune that receptor function in a very precise way.
You got it. Constitutive activity. It's another layer of complexity in in this whole world of receptor pharmacology, but it also opens up some really exciting possibilities for new therapies.
Okay, I'm feeling a little overwhelmed by all this information, but in a good way.
Yeah.
It's amazing to see just how much we've learned about receptors.
I know, and we're not done yet. There's one more key term that I think is really crucial for understanding receptor pharmacology.
Bring it on. What's next?
Let's talk about inverse agonism. Now this one's a little tricky, but it's essential if you want to understand how certain drugs work.
Yeah, inverse agonism. That sounds even more complicated than constitutive activity.
It's related to constitutive activity, actually. An inverse agonist is it's a molecule that binds to a receptor and actually reduces its constitutive activity.
So it's like turning that partially on light switch completely off.
Exactly. An inverse agonist, it doesn't just block the receptor. It actually pushes its activity below its baseline level.
Okay, that's mind-bending. So an inverse agonist, it's like an antagonist, right? But it's even stronger because it's not just blocking; it's actively reducing activity.
Precisely, and this has really important implications for understanding the effects of certain drugs. For example, some antipsychotic medications, they're thought to act as inverse agonists at certain dopamine receptors.
This is incredible. It's like we're going deeper and deeper into the rabbit hole here of receptor pharmacology. I know it's a fascinating journey,
Right.
With endless twists and turns.
Okay, so we've covered a lot of ground here. Let's do another quick recap of these more advanced terms.
Sounds good. It's important to make sure that we're all on the same page here.
So we started with receptor trafficking, the movement of those receptors within the cell. Then we talked about receptor upregulation. That's when the cell actually makes more of a particular receptor.
We also discussed receptor dimerization. That's when two receptors pair up, right?
Yeah.
And that changes their function. And then we explored allosteric modulation, where a molecule binds to to a site that's not the main binding site, right? And it kind of tweaks the receptors settings. And then we went into those really mind-bending concepts.
Yeah.
Biased agonism. That's when an agonist activates some signaling pathways, but not others, right? And then constitutive activity. That's
Yeah.
the ability of some receptors to be active even when there's no ligand. And inverse agonism. That's when a molecule actually reduces that constitutive activity.
Wow, that's quite a list. But thanks to your clear explanations and those helpful analogies, I feel like I'm starting to understand this complex language of receptors.
I'm glad to hear that. These terms they're really really essential for understanding how these drugs work.
Absolutely. They're really the foundation for developing those new and innovative therapies that target specific receptors with greater precision.
This has been an amazing deep dive so far. I can't wait to see what other insights we uncover as we continue exploring this world of receptor pharmacology.
Me neither. There's still so much more to learn and discover, but for now, let's just take a moment to appreciate just how intricate and fascinating these molecular interactions truly are.
Welcome back to our receptor pharmacology deep dive. It's been quite a journey exploring this whole intricate language of how drugs interact with our bodies, at that molecular level.
We've definitely covered a lot of ground, haven't we? From those basic terms like receptor and agonist to more complex concepts like biased agonism and inverse agonism.
It's amazing to think about just how much we've learned about these tiny molecular machines that orchestrate so many of our bodily functions. But before we wrap things up, I want to make sure we kind of connect all these dots for our listeners. What does it all mean? In the big picture, why does understanding all this receptor pharmacology, why does it matter so much?
Well, that's a great question. It matters because it's really the key to unlocking new and better ways to treat diseases. By understanding how drugs interact with specific receptors, we can design therapies that are more targeted, right?
Yeah.
More effective, and they'll have fewer side effects.
Right, it's like like having a toolbox full of specialized tools, right?
Yeah.
Instead of just a hammer.
Mm.
Each tool is designed for a specific purpose, and that lets us make those precise repairs without without causing any unintended damage.
Exactly. And receptor pharmacology, it's not just about, developing those new drugs. It's also about, understanding how our own bodies, how they work at a really fundamental level. It's about unraveling the mysteries of how cells communicate with each other, how they respond to those signals, and how they maintain that balance in an environment that's always changing.
It's like we're gaining a deeper appreciation for this intricate symphony that's it's playing out inside each and every one of us all the time.
Absolutely. And the more we understand the symphony, right, the better we are at identifying what goes wrong when someone gets sick, and then developing strategies to restore that harmony.
So what are some of the most exciting frontiers in receptor pharmacology right now? Where's this field headed in the future?
Well, one area that's generating a lot of buzz is personalized medicine. So by understanding those individual variations in receptor genes and expression, we can tailor treatments
Yeah.
to each person's unique needs and their genetic makeup.
That's amazing. It's like moving away from that one size fits all approach to healthcare,
Yeah.
and creating custom made treatments that are more likely to be effective and have fewer side effects.
Exactly. And there's also a ton of research happening right now on new drug targets. Scientists are constantly discovering new receptors and figuring out what roles they play in various diseases.
So it sounds like there's always more to learn and to discover in this field. the possibilities are really endless.
Oh, absolutely. Receptor pharmacology, it's dynamic and it's always evolving. There's this sense of wonder and possibility that's really exciting for researchers and clinicians alike.
I'm definitely feeling that sense of wonder after our deep dive today. It's been it's been an incredible journey in exploring this hidden world of molecular interactions.
It really has been fascinating, and it highlights just how much we've learned in just the past few decades. But there are still so many mysteries to unravel.
Well, before we say goodbye, I want to leave our listener with one final thought here. We've explored the language of receptors, right? That intricate dance between drugs and cells, and the incredible potential of this whole field. But what about the future of this language? What new terms might be added to our pharmacology glossary in the years to come? What groundbreaking discoveries are waiting for us out there in the world of receptor pharmacology?
Those are fantastic questions to ponder. It's impossible to predict the future with any certainty. But one thing is for sure, right? This field of receptor pharmacology, it's brimming with potential as we continue to explore those intricacies of receptor function and develop new tools to study those molecular interactions. We're bound to make groundbreaking discoveries that will revolutionize how we treat diseases.
That's an inspiring thought. So to our listener, we encourage you to keep exploring, right? Keep questioning, and keep diving deep into this world of science, because the more we understand about how our bodies work, the better equipped we are to live healthier and happier lives.
Well said. And remember, the next big breakthrough in receptor pharmacology, it could come from anyone, anywhere. So keep those minds curious and those imaginations ignited. Who knows? Maybe you'll be the one to discover a new receptor, a new drug target, or even a whole new way to modulate that receptor activity.
Thanks for joining us on this deep dive into the fascinating world of receptor pharmacology. Until next time, stay curious.